Welcome everyone. In this lesson, we're going to start looking at exponential functions. So to get started, let's see how these functions look. And then we'll see how their graphs look as well. And so the general form of an exponential function that we're going to be looking at is a function of this form right here. F of x equal to b raised to the power x. Now, a little terminology. We call this this number here, we call this our base term. And for an exponential function, this base term is a constant. And then where the x is, where our variable is, well, we call that's kind of in the exponent position. So for exponential functions, kind of why they get their name, well, the variable is in the exponent. Now, we've seen other types of functions, and probably the main function we've looked at all through the course so far is power functions. So let's just compare this exponential formula to what we're used to with power functions. All right, so what does a typical power function look like? Well, f of x equal to x raised to the power n. And so if we compare what's going on in an exponential function with what's going on in a power function, for a power function, the base term is variable. That's where our variable is. That's where the x is. And the exponent, well, that's a constant. Maybe call it n here. So that's the main difference between what we're going to be looking at with exponential functions. The exponent is the variable part and the base term is a constant. And with power functions, it's kind of the opposite. The variable is kind of on the main level and the constant term is upstairs in the exponent position. All right, so how do these exponential functions look? Well, the main graph is going to be something like this. And really all exponential functions that we're going to be looking at have this sort of graph. Now this technically is a special case where the base term is greater than 1. So this is the graph of b raised to the power x. Now one common property that all exponential functions have is they all go through the point 0, 1. So they all go through that point right there. And what happens is as we kind of look further and further to the left, they have a horizontal asymptote. So on the left side of the graph gets really close to the horizontal axis, but never touches it. Another interesting property is that for an exponential function, b raised to the power x, it's always positive. It's always above the x-axis. So that means it never crosses the x-axis, never goes below. All right, so those are a couple things. Now, related to this, we can kind of have like a graph for the mirror image. And there's a few ways to think of this, and probably the one we're going to see the most common is this is the graph of b raised to the negative x. And so what happens is it's really just the kind of the mirror image of the previous graph. Same properties. It's still going to have a horizontal asymptote as we get closer and closer, as we'll get closer and closer to the x-axis over here, but it's now on the right side. and it's still never going to cross the x-axis. And it still goes through that point 0, 1. Okay. Now what happens if we kind of look at the graphs for a few different specific types of exponential functions? So here I have plotted a few different exponential functions. So here we have 5 raised to the power x. The next one is 2 raised to the power x. And then down here we have 1.2 raised to the power x. And then kind of trivially, we have 1 raised to the power x. And it's just a horizontal line. And what you see is that what's in common with all of these is that they all go through that point 0, 1. So they all go through that point. And what are a few other properties? Well, again, they all except this one with 1 greater than x, or 1 raised to the power x. That one's just a horizontal line, so we don't really consider that an exponential function. Normally, it's when we think of exponential functions, we're thinking of numbers bigger than 1. So, but what we notice for all these exponential functions that are bigger than 1, they all have horizontal asymptotes at y equals 0. So they all get closer to the x-axis, and they never actually touch or cross the x-axis. Now, one other thing is that if the base term is large, so notice that for 5 raised to the power x, it's larger than these other two. What happens is right at this point, the curve is steeper. The tangent line, it has a steeper tangent line. So what happens as b gets larger, the slope at x equals 0 gets larger. And for small b, so for values of b that are close to 1, we're going to have kind of a smaller slope at x equals 0. And so this idea of considering the slope of these exponential graphs at x equals 0 is going to be important later on. But you can kind of see this. If we go up, for 5 raised to the power x, it's going to have a steeper slope. And then for, say, 1.2 raised to the power x, the slope isn't going to be as steep there at x equals 0. All right. So it's going to be important. We're going to be working with exponential functions quite a bit. So it's going to be important to review some of our exponent rules. And these are ones that we've worked with so far in the course, but it's definitely going to help to review these. So let's kind of read through what they say and talk a little bit about these. So for the first one here, we have b raised to the power x times b raised to the power y. And what we can do, when the base terms are the same and we have different exponents, we can combine them into one single exponential term where we add the exponents. So that's going to be important. We need to have the same base. So the base term has to be the same in order for this property to work. And essentially what happens is it converts multiplication into addition. Now we have this other property, and we've used this one quite a bit. When we have a negative exponent, we can convert that into a fraction by just taking the term and making that into the denominator. So in this case, 1 over b raised to the x. Or we can go backwards. So if we have a fraction, if we make the exponent negative, then we can get rid of the fraction. So we've kind of used this one a bunch of times already. Another property is if we're dividing. So if we have b raised to the power x divided by b raised to the power y, Well, we can convert them. We have two different exponential terms. We can convert it into one exponential term where essentially the division becomes subtraction up in the exponent. And again, this is another one where this only works if we have the same base term. So we have base b, base b, base b. Another property, if we have an exponential function or exponential term getting raised to another power, what we can do when we have multiple exponents like this is we can multiply the exponents. Now, the last two properties here are almost like distribution. They're almost like a distribution property. So if we have a times b raised to the power x, what this property essentially tells us is we can take that exponent and we can distribute it to each of those terms inside the parentheses. Or you can think of it like a factoring. So if we kind of read this the other way, if we have two exponential terms that both have the same exponent, well, we can essentially we can factor off that common exponent. And same thing for division. So for each of these, though, we need the same exponent. So notice that over here on the left, both of our exponential terms were being raised to the power x. And so we were able to factor off that power x. Same thing here for our fraction. If we have two exponential terms both raised to the power x, well, essentially we can factor off that common exponent. So we have a couple properties here that tell us what to do if we have the same base. And then we also have a couple properties that tell us what to do if we have same exponents. There's some algebraic properties that we can work with. Now, one important thing to note is, and it's always tempting, is that these last two properties, they only work for multiplication and division. So if, for instance, rather than having, say, a times b, like we have down here, a times b, say we had a plus b, all raised to the power x. Well, that does not equal, usually, a raised to the power x plus b raised to the power x. Same thing with subtraction. So if we have a minus b raised to the power x, usually, so it's not true in general, we can't distribute the exponent over addition or subtraction. So it only works if we have multiplication or a fraction or division there. All right, so let's try a few examples just to get a little practice with using these. So in example 1, and we're probably not going to do all of these, we'll save some for class time. But for this one, we're going to use the exponent laws to write each of the following expressions in the form 2 raised to the power kx. So we have all these exponential terms, and essentially what we're going to do is try to combine them into just one exponential term. We're going to use all of our properties so that we can simplify this down as much as we can. All right, so let's look at this first one. We have 2 raised to the power 4x times 2 raised to the negative x, and then this whole thing getting raised to the power 1/2. All right, so to start, where could we start with this? Well, I might start with looking what's in the parentheses here. So what do we have? We have 2 base terms that are getting multiplied together, and they're both base 2. So let's go back to our properties. Which one of these exponent laws can we use if we have the same base and they're getting multiplied together. And which one? Let's see. Same base. Here we go. And we're getting multiplied together. So we can use this first property. All right. So let's see how this is going to work. So we're going to have our 2 raised to the 4x. And since we have the same base term, what we do is we add the exponents. So we're just going to add in negative x. Okay, well, now just do the regular arithmetic here. 4x plus negative x is going to simplify to just 3x. And then, well, where do we stand now? We have 2 raised to a power 3x, and then that whole thing getting raised to the power 1/2. So we have multiple exponents. So the next property we can use is our multiple exponents property that says, well, just multiply the exponents. So we're just going to multiply the 3x with the 1/2. And that gives us 2 raised to the 3/2 power times x. All right, so which properties did we use? Well, for the first step, we used property 1. So I'm not going to expect you to have the ordering of these properties memorized. Excuse me. But just for your notes, we use property 1 right here. And then we use property, which one? 4 for our last one. All right. So what we were able to do essentially is we were able to take this kind of complicated expression and we were able to simplify it algebraically, so we got it down to this form, this single exponential function, 2 raised to the 3/2 power times x. And so essentially what we were able to do is we were able to write this 2 raised to the 3/2 power times x. And what this tells us is that the constant k, in this case, the number in front of x, is 3/2. All right, let's try another one of these. So again, we have a kind of complicated exponential term here, or terms, and we want to simplify this down as much as we can. All right, so what do we have? Well, when I look at this, we have 10 raised to the power x divided by 5 raised to the power x. All right. And we want to, for this one, we want to get it into the form 2 raised to the power kx. I don't see any 2's yet. But what I do see is that both of them have the same exponent. They're both raised to the power x. All right, so let's go up. Which one of these properties, first of all, involves a fraction? So, you know, maybe this one, but I don't see, we don't have a 1 on the top of our fraction. This one involves a fraction, but in this one, the base terms have to be the same. So that really doesn't apply, because what do we have? We have a 10 and a 5, so that doesn't really work out. But the last one here, I also have a fraction, and the base terms can be different. So we can have different base terms, but we need to have the same exponent for this one. And let's check. Yeah, we do. They both have the power x. So the exponent is x there. So essentially what we can do for this one is we can take off the powers of x. We can think of it like factoring off the exponent there. So we can write this as 10 raised to the power 5, all raised to the power x. So this is property 6. So we can factor off the exponent. And the only way we can do that is if the exponent is the same. And in this case, it is. All right, so then we keep going. Now let's simplify what's inside the parentheses. And there we go. 10 divided by 5 is 2. All right, so to answer the question here, I mean, that's pretty good. But I think there might be a homework question where you have to just state what the k value is. Normally we won't, well, I shouldn't say that. There will be instances to be able to kind of look at an exponential function and kind of figure out this k value. So if we're looking at this one, 2 raised to the power x, well, there's really like a hidden 1 in front of that x. So normally we wouldn't write this, but we could. We could write this as 1 times x, or 2 raised to the power 1 times x, which is telling us that the number in front of x is 1. All right, so we're going to try a few more of these in class. And where we're going with this is all going to lead to the natural exponential function, which is one of the really nice functions that gets used quite a bit in calculus. And we're going to see why next time, or we'll see why in class. So we'll see you there. Bye-bye.